everyone, and welcome to our new discussion which is on atmospheric errors and corrections under this remote sensing essential course. Earlier we briefly touched about this issue, but today we are going to discuss in depth the reasons for atmospheric distortions and then how these are reflected in our satellite images. And finally, we will also see what are the possibilities of getting rid of atmospheric distortions. So, as you know that between satellite and earth surface there is atmosphere, but if atmosphere is very thin or would have been thin, then that should have been delight for us, or for any remote sensing people. But unfortunately, it is not true in case of earth, and though it is very important for life, so it is fine. But if we think about Mars, then Mars is having very thin atmosphere, and therefore, though it is written here the geologist delight, but does not mean only for geologists, for engineers or anyone who uses remote sensing data. And because there are no clouds and the atmosphere is very thin, and therefore we get almost a transparent atmosphere and a very thin atmosphere and very clean satellite images. From morning to evening, through the reflection or sunlight, we get very good images, but this is not true in case of earth. And the whole radiation spectrum of remote sensing is also available if no atmosphere or very thin atmosphere is there. As mentioned that in case of earth, all radiation passes through or pass through a dense atmosphere, relatively dense compared to Mars, and because a sensor or reception or a satellite earth station is located on the ground, so this has to be also incorporated the reasons or effects of atmosphere. So, the solar radiation must pass through the atmosphere and then back again to the sensor. So, this creates a lot of problems in the satellite images, and sometimes when it is cloudy, that is also atmospheric phenomena, then you completely clouds completely will mask the land part and you do not see anything of the land. So, this kind of complication is there, and as we know that for a sensor measuring radiation emitted by earth in case of thermal infrared, the path is single, not double in case of reflection or solar based radiation, because sunlight will come, it will interact with the atmosphere, and then when it reflected back by the objects, it goes back again. And third time also a role of atmosphere is there when the data is being received by earth station, but at that time because the data in the microwave part, so it does not affect much, but still there are roles are there. And for a emitted part, only the single path, because whatever objects are emitting energy, that is being sensed by the sensor, but nonetheless it has to also pass through the atmosphere. This figure we have used in very early stages of this course, and that is the interaction with atmosphere, and it is a accounting of radiation. So, as we know that between earth and sensor there is atmosphere, and there might be sometime clouds which absorbs, which also reflect, and then the cloud themselves may emit energy. So, when we go for emitted or thermal infrared, then clouds also play important role. Thick clouds can be detected very easily, but when you are having very thin cloud or haze or that kind of thing, then it becomes very your images becomes unclear, and removal of such effects also becomes very challenging. So, as we know that if 100% of we count 100% incoming solar radiation, then 47% of that is absorbed by the earth, and 17% is absorbed by the water vapor which are within the atmosphere, 4% is absorbed by the cloud, and these are just rough estimates, and this is a very dynamic, atmosphere is a very dynamic thing, so things keep changing, but on average, and then 6% is back scattered of that 100 back to the atmosphere or in space, and then 19%, a large part is reflected. Only 4% is absorbed, whereas a large part, that is 19%, is reflected by clouds if they are there. Also water bodies also reflects, maybe lakes, maybe rivers or sea part, so they also reflect a lot of energy. And then if we go for a long wave part of energy, then what we see that there is a long wave radiation from the earth, which is going out in case of thermal infrared. So absorption by the cloud, water vapor, carbon dioxide. Here emission 20% by clouds, emission by water vapor, carbon dioxide, etc. They also contribute. So lot of long wave radiation is coming, but it is getting disturbed or absorbed, reflected, basically absorbed, emitted by the atmosphere itself. And of course, the heat which has been absorbed earlier, 47%, is transmitted back by the land, that is latent heat transfer, and which goes into the space. So this is this tells us that how many processes are going on between a satellite and surface of the earth and within the atmosphere. And therefore, that is why I said that in order to remove these distortions, it is really challenging, because one, the atmosphere is dynamic, and second is so many processes are going on, emission by within the atmosphere, reflection within the atmosphere, and absorption within the atmosphere, and that too depending on the conditions, other conditions, maybe the wind speed or maybe the moisture content and temperatures also. So all these things makes very complicated this part. Nonetheless, this in percentage we have already discussed. So in short, it is this figure in a simplified form, and before radiation, especially for what we are talking about for remote sensing, that reaches towards the earth, it has to travel through some distance at the earth atmosphere, and the particles and gases which are present in the atmosphere can affect incoming light and radiation. So we are concerned mainly with the radiation directly. Of course, when the whatever it is going back, at that time also it will have a problem. So these effects are caused by mechanism of scattering and absorptions, and we also know that if we see this, some part of EM spectrum is displayed here, and this is spectral radiant emittance, and we find that these are the water and gases which are absorbing a lot of this radiation, and therefore it becomes very difficult in that way. The visible part is up to only this much. So nitrogen, oxygen, which are present in the atmosphere, ozone also present in the atmosphere, and carbon dioxide. So many these gases will absorb and may not provide a clear, ultimately may not provide a clear remote sensing image. So all this interactions with radiation by vibrational and rotational transitions, and then net effect of which is the absorption of energy in specific wavelengths, which you can see here, that how water, if you see H2O, it is almost in every part of EM spectrum, this part especially which is being displayed, every part there is a absorption, almost every part. So the moisture or water within the atmosphere having lot of absorptions in different part of EM spectrum. So other gases, but their roles are limited and not everywhere. like ozone plays very large absorption in case of visible, but in other parts it is not that common. So, what is that process? Atmospheric correction is the process of removing the effects of atmosphere on the reflectance values of images taken by satellite or airborne sensor. Here it has been mentioned the reflectance value. These values can be also emittance value. So, the atmosphere correction is the process of removing the effects of atmosphere, and as I have already said that this is because of complications within the atmosphere about the radiation, this is real challenging. So, large amount of images, as we know, are being collected by satellites, have already been collected by various satellites of various countries, and these are largely contaminated or affected by the atmosphere or the particles which are present and gases, and almost all images are suffering from either absorption, scattering, and that is of the radiation of the Earth's surface. So, you see any image which will be having some effects of atmosphere. Let me give you one example. After like in during monsoon time in India, or especially in the winter monsoon time, after just after the rain, when sunlight is there, even our visibility along the horizon increases very significantly. So, think if at that time a satellite is overpassing, it will acquire a very clear image. Why? Because the rain will reduce this absorptions phenomena or absorbing materials from the atmosphere, because there might be the dust particles, there might be aerosols and some other thing which are present, and all these because of rain they will come on the ground, and therefore atmosphere becomes very clean. So, sometimes just after the rain, if one is lucky and a satellite is overpassing, one can get a very clear image, and clear image means it is suffering from less atmospheric effects, less because of absorption and scattering. Once these particles are only little are present, then obviously the scattering and absorption would be less, image would be clear. So, this can be seen even on the ground just after the rain if sunlight comes there. So, basically the main purpose of atmospheric correction is to retrieve the surface reflectance, basically minus distortions and induced by an atmosphere, and this characterizes basically these surface reflectance, which characterizes the surface properties from remote sensing images by removing atmospheric effects. Now, there are different approaches. Some are implementable easily, and some are very difficult to implement because of lot of input data is required. So, correction approaches, some are sophisticated approaches, as computationally depending, and have only been validated for a few small scale studies. If I want to do it regularly on all the images, it is not possible. So, that is why I have been using word challenging for removing 100% removal of atmospheric distortions. Though there are algorithms, lot of algorithms are there, models are there to remove these atmospheric distortions. Two major steps which are done through these algorithms is, the first one is the optical characteristics of the atmosphere are estimated, and how these are estimated? Using special features of the ground surface or by direct measurements of atmospheric constituents or by using theoretical models. Now, we will spend some time on this particular sentence here. If there are special features on the ground, that means if you are having some object which are having very high reflectance, very high albedo, then you can take that one as a one of the reference. How? Suppose you are having a patch which you expect that it should be having in 8-bit image scenario, it should be having highest reflection close to say 255. Suppose it registered reflection in the pixel is 250. So, after seeing the image of that pixel, I know that because of absorption the remaining 5 value has not come. So, that means if I adjust by 5, then probably I have got rid of atmospheric distortions. So, using spatial features, now every image cannot have spatial features, because images are being acquired regularly, and whenever there is revisit of satellite, and various satellites are involved. So, it is very hard in practical terms that we get a spatial feature present within the image. So, this possibility is very rare. However, this is one way of getting rid of atmospheric correction. Second one is by direct measurement of atmospheric constituents. So, if you are having some other method, meteorological stations or profiling or other things, by which you know that what is the concentration of aerosols, what is the concentration of different gases which are creating distortions in different part of EM spectrum, absorption and scattering. And if that information of that particular time when satellite image was acquired, if that is available, then this technique can work very well. Again, it is very difficult because all the time satellite are overpassing, and too many inputs are required about atmospheric constituents for that particular time when image was acquired. So, this itself is also very challenging. Now, third one, the most popular one, is using theoretical models. And if you go, the demerits about this, that everything is fixed, but same time we know the atmosphere is very dynamic. So, theoretical models may also bring some level of corrections, atmospheric distortions corrections, but not fully. So, the problem lies here because of all these complications which are present within the atmosphere. So, various quantities, that means the atmospheric constituents to the atmosphere correction, can then be computed by radiative transfer algorithm given the atmospheric optical properties. And another one, that the first approach was like this, the second approach can be that corrected by inversion procedures that drive the surface reflectance. So, again when we go for inversion, again lot of things will be assumed there. Anyway, this is one way of, very quick way of getting rid of atmospheric distortions without bringing any more data or many more inputs about atmospheric constituents, assuming that within this image I should have the full dynamic range, pixel values occupying the full dynamic range in 8-bit scenario, that is 0 to 255. So, like when I see this image and the corresponding histograms, what I see that this is also, recall I also discussed the LUT, lookup table. So, now lookup table is being used here. So, on the y-axis, this is the input histogram. As you can see, it is restricted into the very beginning values, only up to maximum value is up to 100 and minimum value is around 40. And therefore, the image which you are seeing here, this image is completely black, because it is not occupying the full dynamic range which is available between 0 to 255. Assuming that this image is having some high reflection, because these clouds are taking that part of histogram, or other absorptions phenomena are creating, are taking this begin part of my histogram, it means lower values, and this reflection by the cloud are being occupied by the higher value. So, we assume that this is the situation. That means I can, if I stretch it, linearly stretch it, then what I am going to do it, I will occupy the full dynamic range, that is in 8-bit scenario between 0 to 255, and my image may become something like this. So, also it is shown in the lookup table that as soon as it touches here, then it is just going to the top, that is 255 value. So, two things are here. One is atmospheric correction by a sort of simple linear stretch or contrast stretch, and second thing is also use of lookup table. So, this is example of Landsat TM3 band on the left side, and this is of the Sudan Eritrea border, and you can realize that how quickly one can get rid of atmospheric correction by applying simple linear contrast stretch. But these will also this method is a sort of a brute force method. If there is no information or input from atmosphere, so whatever the atmospheric conditions, we have not bothered and just got rid of these corrections. So, this is again, this cannot be a standard for atmospheric correction, but when we do not have much data, input data available, neither a specific feature of the ground surface, nor we do not have or atmospheric constituents or theoretical models, then this is the quickest way of doing atmospheric correction. Now, so atmospheric correction consists basically of two parts. One is the estimation of atmospheric parameters. So, this is again estimation. Lot of assumptions would be there, and retrieval of surface reflectance, and if the surface is Lambertian and all the atmospheric parameters are known, then remote sensing images can be calculated to directly retrieve the surface reflectance. And so, these are the conditions. So, based on radiative transfer theory and assuming that the target is in a uniform Lambertian surface, and then the radiative radiance can be received by a sensor or can be estimated, assuming that a sensor is getting like this, and that is the top of the atmosphere TOA, and which can be expressed as L0 plus rho 1 minus S rho and multiply by TF d by pi. So, where L0 is the atmospheric radiation path, which in case of no surface reflection, and T is the transmittance from the surface to the sensor, and the S is the atmospheric spherical reflectance, rho is the surface target reflectance, Fd is the downward radiation flux reaching the surface, and according to this equation, the radiative received by sensors are given by L, L0, S, TF, and rho can be calculated by radiative transfer model and used to calculate surface reflectance. So, as at this stage you can realize that so many parameters are required, and which are those parameters which are dynamic, and that creates some problem anyway. So, for atmospheric correction models and softwares what are available today, because everyone will not be developing their own models for atmospheric correction and neither coding things. So, what are currently what is available. So, for most atmospheric correction algorithms, it is necessary to solve radiative transfer equation and establish, as just we have seen, establish lookup tables, also we have seen one slide back, for rapid atmospheric corrections, resulting in a series of atmospheric correction models, and which is based on the theory of atmospheric radiative transfer. And these models like MODTRAN, moderate resolution atmospheric transmittance and radiance code. Now one more issue or intricacy is coming for a moderate resolution, because resolution high, moderate or coarse, these are all relative terms. So, what was moderate yesterday is coarse today, and what was high yesterday is moderate today. So, nonetheless, not for very high resolution satellite images, but moderate resolution satellite images, there is a model which is called MODTRAN. But when we go for very high resolution images, because the area, the swath becomes very small, and therefore, getting input data only for that part of image becomes further difficult. But when we go for coarse or moderate resolution satellite images, then somewhere at least within that image I might be getting those atmospheric data. So, that is why for fine resolutions it is another problem. Then there is a 6S, and other atmospheric radiation approximation calculation models are also available. Now, usage of these models and software is complex, and that is why I said that not everyone would be developing their own, and therefore, there are interface based atmospheric correction software packages are available, and which are like FLAS, Actor or Acorn, or maybe few more one can find, but which one will provide the best results, it is very difficult to say unless one applies on his own data set. So, based on the MODTRAN, one example that these models are constructed from a large number of lookup tables for convenient and rapid atmospheric corrections for a variety of sensors. Very briefly, we will also see what is this MODTRAN. Basically, it is used to calculate atmospheric transmittance and the radiative transfer algorithm with moderate spectral resolution data. And MODTRAN can be used to calculate atmospheric transmittance, atmospheric background radiation, and the radiance of single solar or lunar scattering, direct solar irradiance, and likewise. And MODTRAN was based on LOTRON with a spectral resolution of 1 per centimeter. So, earlier version was LOTRON, basically it was for low resolution or coarse resolution, then moderate, maybe in future we may have HITRON. So, the input parameters for the operation of MODTRAN can be divided into 5 types. Lot of input parameters are required. First is controlling and operating parameters, atmospheric parameters, that is atmospheric parameters and surface parameters. That means somebody has to be present with all kinds of recordings of atmospheric data of that part of the earth where image will be acquired by a satellite. So, then the current atmospheric parameters and that time corresponding surface parameters will be required. Then observation geometry, how these have been observed, sensor parameters, of course, that is these are the fixed part, observatory, and these are the fixed part, but the other 3 are required corresponding or at that time of required. So, the main output, the result would be from MODTRAN is simulated apparent radiance, and it will give the simulated apparent radiance that can be used further by those software which just I have mentioned, and then atmospheric corrections can be done. One example is here, before correction on the left side and after correction on the right side, and this is example for Landsat TM images, and we are seeing in color. So, 3 bands 1, 2, 3 have been used in RGB scheme, and this is what you see that mainly in the central part, top central part, you are seeing effects of atmosphere, maybe because of thin clouds and others, and that effect or distortions have been minimized in the right side image. So, atmospheric correction has shown significant improvement in the accuracy or visible interpretation of that satellite image. Now, there is one more point here. As long as one is using satellite images for qualitative analysis and assessment, not many problems are there. But once we go for quantitative analysis of satellite data, then it is a problem. For example, if I am a scientist or civil engineer and I am using satellite images to identify certain objects, create a land use map, maybe a lithological map, or for some other studies where I do not require quantities, I just require the clean image so that my interpretation becomes much easier. So, for those purposes not much atmospheric correction or no atmospheric correction would be required. But if I go and would like to find out how much concentration of a certain pollutants in the water, or what is the real what is the chlorophyll content in the vegetation, then definitely I am moving towards the quantitative analysis of remote sensing data, and that means I have to perform atmospheric correction too, without which it is not possible to estimate those things. So, this is what is as long as the remote sensing data is being used for qualitative analysis, then it is rather easy and straightforward, as I have just mentioned and given example. But when we employ for quantitative analysis, then all kinds of complications will arise, and as can be seen in atmospheric correction. And therefore, if remote sensing data is intended for only for qualitative analysis, then that brute force method or linear contrast stretch method can be employed, and it will give you a better quality image, which is sufficient for the purpose which we are using the satellite images. So, in that way it becomes much easier. So, this brings to the end of discussion, but in summary what I would like to tell, that atmospheric correction performing, because it is a complex atmosphere itself is a complex and dynamic phenomena. Lot of parameters are required to correct or remove these atmospheric distortions, and especially those parameters are required of that time when satellite image was being acquired. So, corresponding data is required, and it becomes very difficult to go in the field and collect all that data for the full extent of the satellite image. Therefore, some model based atmospheric corrections have become popular, or brute force atmospheric correction. If quantitative analysis are not intended, then brute force or simple linear contrast stretch can also improve your image quality. Though there are some non-linear contrast stretches are also there, one can also perform and visualize that whether the quality of an image has improved for better interpretation and not, and that can also be acceptable or can be accepted for such kind of applications. So, this brings to the end of this discussion. Thank you very much.